Okay, listen to this for a second. Brief audio clip plays. That sound, that's basically the Earth speaking.
In a way most people have never heard before, yeah.
Exactly. Welcome to this deep dive on All Sorts podcast. We've pulled together some really interesting source material, and our mission today for you is to dig into the most compelling bits. We're focusing on how we can listen to the planet's vibrations using something called seismic sonification, turning earthquake recordings into sound.
And it's a fascinating field. We're going to explore how turning these seismic waves into something we can actually hear gives us new ways to understand Earth.
Right. And we've got some great sources lined up.
We do. There's a study from Lamont Doherty Earth Observatory, published in the International Journal of Human-Computer Studies. Also an article from eos.org, some work from Leandro Pisano called Seismic Soundscapes, and research from Nagoya University on synthesizing earthquake sounds.
Okay, so we usually see seismic data, right? Those wiggly lines on a seismograph.
The classic image, yeah.
But this eos.org article raises a really interesting point. What if we used our ears instead? Or maybe alongside our eyes?
It turns out our hearing is actually surprisingly good at picking up patterns over time.
Better than our eyes sometimes?
In some cases, yeah.
Yeah.
Especially for things like cause and effect, subtle changes. And think about the potential there.
For scientists, obviously, but also making this accessible.
Exactly, making it accessible to more people, including scientists who might be visually impaired. Their auditory skills might even give them an edge.
That's a really powerful thought, just opening up another sense to this data.
And it's not like this idea just popped up yesterday.
Oh.
No, the International Journal paper points out that a seismologist named Hugo Benioff was already playing around with this way back in the 1950s.
50s? What was he doing?
Get this, he actually released an LP record, a whole album of sonified seismograms.
An earthquake album. I love it. Did people buy it?
Well, it was commercially released.
Yeah.
And the paper mentions there was even an early idea floating around that maybe just by listening, you could tell the difference between a natural earthquake and something like an explosion.
Like a sonic fingerprint. Wow.
Sort of like that, yeah. Now, that specific idea didn't quite pan out with modern digital analysis taking over, but the core concept stuck around.
Which is?
That there's real information baked into the sound of these seismic events.
Okay, so how does it actually work? How do you turn ground shaking into audio? The Lamont Doherty study looked into this, right?
They did. And the basic idea is time compression. Seismic waves vibrate really, really slowly, way below what humans can hear.
Like deep bass sounds, but even lower?
Much lower, so you speed up the recording. A lot.
How much is a lot?
In their experiment, they were playing signals back about 150 times faster.
Whoa! So hundreds of seconds of an earthquake become just a few seconds of sound.
Exactly, condensing that long rumble into something short and, well, audible.
Okay, so they did this with an Oklahoma earthquake, magnitude 5.6.
That's the one. And they recorded it at 17 different seismic stations. Then, as the paper describes, they got volunteers.
What kind of volunteers?
People with backgrounds in earth science, or acoustics, sound engineering, a mix. And they played them these sped-up earthquake sounds.
And asked them.
Here's the clever part. They didn't tell them what to listen for. Just asked them to group the sounds that seemed similar. They called it free categorization.
Just based on instinct, almost. What did they find? Could people actually group them meaningfully?
Yeah, they really could. It was quite striking. The groups people made tended to match up with real physical things.
Like what?
Like how far the station was from the earthquake's epicenter.
Really? You could hear the distance.
Or the direction, the azimuth, from the source to the receiver. Even hints of the geology the waves traveled through.
Just from the sound. That's incredible. It suggests our ears can pick up on these complex details without us even consciously knowing what we're listening for.
It really does. It taps into this maybe intuitive pattern recognition we have through hearing.
So much information we might be missing if we only look. Now, you mentioned normalization earlier. Why do they need to normalize the sound?
Ah, right. Well, seismic signals have a huge dynamic range. The difference between the quietest background rumble and the peak shaking can be enormous.
Much bigger than audio usually handles.
Way bigger. Our ears just can't cope with that full range comfortably. So you normalize the signals, often scaling them so the loudest part hits a certain maximum level.
Okay, so everything gets brought into a similar volume range?
Pretty much. But here's a subtle point. Even though the peak volume might be similar after normalization, the clarity changes.
How so?
The signal-to-noise ratio. It generally gets better the closer the station is to the earthquake.
Ah, so closer events aren't necessarily way louder in the final sound, but they sound cleaner, less noisy.
Exactly. More distinct, less muffled by the background noise. It's about fidelity, not just raw loudness.
Got it. Now, you also mentioned the Nagoya University research. They have a different approach, not just speeding things up.
Yeah, they're working on sound synthesis. They use some clever math-symmetric Fourier analysis to basically generate a sound based on the seismogram's frequency information.
And the goal there is?
To create a sound that actually lasts the same amount of time as the original earthquake recording.
Oh, okay. Not compressed.
Not compressed in time. In their method, the pitch you hear relates to the wave's instantaneous frequency, how fast it's shaking at that moment, and the volume relates to the overall strength, the envelope amplitude.
And they've built tools for this. You mentioned Neon and Everest.
Right. Neon is cool. It's web-based. You can upload your own seismogram data, and it generates the sound using their method.
So anyone can try it.
Pretty much. And Everest is more involved. It's an audio-visual system. It combines their synthesized sounds with visuals, like simulations of buildings shaking.
Wow, trying to create a more complete experience of an earthquake's impact.
Yeah, making it more tangible, more understandable.
They also talked about educational tuning. How do you tune an earthquake sound to be more educational? Sounds a bit funny.
Huh, yeah, it does. But it's about making the important information easier to grasp through hearing.
Like what?
Well, for instance, using a logarithmic scale for frequency. Our ears perceive pitch logarithmically, so mapping the seismic frequencies that way makes changes more noticeable across the whole range.
Okay, makes sense. What else?
Using richer tones, maybe like musical instrument samples instead of just plain sine wave beeps, makes it less harsh, more informative texturally.
A bit more pleasant to listen to, perhaps?
Maybe, yeah. And another neat idea is about volume. Instead of just using the overall envelope, which can make long, slow shaking sound unnaturally constant.
Right.
They suggest using the absolute value of the ground motion itself for the amplitude. That way, the volume more closely reflects the actual ups and downs of the shaking, even for those long period waves.
So really refining the translation from data to sound, trying to preserve as much useful info as possible.
Precisely. It's all about effective communication of the data through audio.
Let's circle back to that eos.org article. They had that great example with the Kilauea volcano combining sound and visuals.
Ah, yes. The data movies. That's a brilliant application.
How would that work?
They took multiple streams of data, seismic tremors, ground tilt, gas emissions maybe, and represented them simultaneously.
So you could see, say, the ground swelling on an animation.
And at the same time, hear the corresponding seismic activity ramp up through sonification.
Ah, so you engage multiple senses to understand complex relationships.
Exactly. It makes it much easier to spot correlations, to see and hear how different processes are linked in time. Really powerful for understanding dynamic systems like volcanoes.
And it's not strictly limited to science or education, is it? There's an artistic side, too. Leandro Pisano's Seismic Soundscapes.
Absolutely. There's definitely an artistic dimension. These are, after all, the fundamental vibrations of our planet.
Pretty profound source material for art.
It really is. Projects like Pisano's take these sonified sounds and use them to create immersive experiences, installations, compositions, exploring the emotional and aesthetic resonance of Earth's sounds. A whole different way to connect.
So wrapping up this deep dive then, it feels like seismic sonification is, well, much more than just a neat trick.
Oh, definitely. It's a genuinely valuable tool.
It offers this completely different sensory channel for understanding Earth processes, potentially revealing patterns we might miss visually.
It aids discovery, broadens accessibility. It just opens up new ways of interacting with the data. We're literally learning to listen to the Earth.
It makes you wonder, by lending our ears in this way, what else might we start to understand?
It's a compelling question, isn't it? What hidden stories are waiting in those vibrations?
And you, our listener, you've journeyed with us into the sonic landscape today, so think about it. How does hearing the planet move, rather than just seeing graphs, change how you perceive it? What other silent signals around us might reveal secrets if we just found the right way to listen?
It's definitely food for thought.
It really is. And just as the Earth hums with these untold stories waiting for curious ears, All Sorts Podcast thrives on your engagement, on you exploring these fascinating topics with us. If this deep dive into the sounds of our planet resonated with you, If it sparked something, then let us hear from you. Head over to All Sorts Podcast on YouTube. Show your support, like, share, subscribe, join our community.
We appreciate it.
We really do. And remember, our archive's full of other explorations waiting for you. Follow All Sorts Podcast on X, Instagram, and Threads too. Let's keep learning together across all sorts of fascinating topics.